In this video, we will look at electromagnetic waves and more properly how these waves are generated. I'm going to put here E&M waves, change to the black color. So E&M waves or electromagnetic waves. Let's start with, we will only go over the concepts here. I'm not going to introduce any math with this. We will just go over the concepts. And if you're in my algebra-based physics class, there will be some calculus here in the sense that I'll show one or two equations, but we won't do anything really with them. You can just ignore that part when it shows up. Just follow the concepts. So before we start anything here at all, you have to recall that if you have a magnetic field, let's say the magnetic field points in this direction, if this magnetic field varies with time, if it's a time-varying magnetic field, then from Faraday's law, you will obtain that. Actually, I don't even have to state, I don't think I'm going to state the equations. It's going to be the Faraday's law, and there's a specific version of Faraday's law, the integral version, or for that matter, the derivative version actually works better. I think the derivative version is more intuitive to grasp. It's the one with the curl of the electric field. In any event, if you have a magnetic field and this magnetic field is changing, it's varying in time, then you will find out that you have an electric field. An electric field curls around this thing and does something like this. So it goes around, and I'll draw another one. Here's the electric field. The electric field is present everywhere here in this space, and it just curls around. I'm going to add one more, but I'll just draw it like this. So here's the electric field. If there's a magnetic field and the magnetic field is changing with time, then you will end up with an electric field that is present along with that field. This is something that we can show with mathematical equations, Maxwell's equations, and we can also measure this and observe it. So what we have out of this is that if you have a time-dependent magnetic field, then you will also have an electric field that is present, and there doesn't need to be any charge at all in the picture. You will still have electric field. Likewise, if you have an electric field, now let's say the electric field points like this. Could have just drawn a straight line, but anyways, and the electric field sits there, but it changes with time. This is a time-varying electric field. Then you're going to end up with a magnetic field. And this is the Ampere's law, and it's easier to see the geometry of the Ampere's law if you look at it in terms of the stated in a derivative way. But anyways, you could use the right-hand rule here as well, and then you'd see that the magnetic field would just curl around this thing. So here's the magnetic field B, and I should probably draw it the same way I did the electric field, so there would be a magnetic field that curls around. So maybe I'll do one more. Here's the magnetic field that curls around the changing electric field. And so if you have a time-varying electric field, then you're going to end up with a magnetic field present in the space as well. And there doesn't have to be any magnets. You don't need any magnets in neither one of these two pictures. From this and from this, generally speaking, if you have a changing magnetic field, you end up with an electric field, and if you have changing magnetic field, you end up with an electric field. So keep this in mind, right? I'm going to box this. If the pictures that I drew don't ring any bells, that's not the end of the world. Just keep in mind this statement and this statement. So consider a charge. Now let's look at how these electromagnetic waves are actually produced. So consider a charge. Here's a charge, Q, and we're going to say this is a positive charge. This positive charge will have an electric field. An electric field, we know how it points. It just points away like this, and then points away like this. Points in this direction, and it points in this direction, and it points here, and it points here, and so on. Here's your electric field of a charge, and if this charge is not moving, the story ends there. This is all you have. But now suppose that you take this charge and you move it downwards. So what will happen is, let me extend these. And I'm going to copy part of this picture to the right. All right, so I've copied the same picture and I put it slightly to the right. Now let's cause this charge to move downwards. So now let's move this charge down. As I move it down, something like this ends up happening. So the charge has moved downwards. Well, I guess it will have to do for our purposes. It's good enough. Let's leave it here. And now I want you to observe what just happened to the electric field. Now the electric field cannot just sort of snap in space like that. I mean, actually it can, but it won't have, this won't happen here. So if the charge does in fact move downwards, then what happens is some of that field remains where it was, but then you would have to end up with this kink here. It looks like that. Here's the kink. Let's connect this. That stays where it was. Here's the kink, and then here's another kink like that. Let's connect it all. And that just sort of points this way. Okay, that's not too bad. So this is what I have. So the electric field near this charge will just maintain its shape, but farther out, the electric field will have these kinks. And this is sort of the beginning, in a sense that as you make this charge move lower, and then you stop and you bring this charge back up and you let this charge oscillate back and forth, back and forth, back and forth, what will happen is these kinks here, they will start to overlap. And as they overlap, they will start to form these loops. So this kink here will overlap with the next one, this one will overlap with the next one, and they'll form these loops. Now I'm going to show you an animation of this so that it perhaps makes a little more sense. Now I'm going to come back to this picture. Okay, so what we have here is a FET simulation where we have the charge in the middle. It's a positive charge, and then these lines here indicate these are the lines of the electric field. So if I take this charge and I move it down and up, I get these kinks that travel outwards. This is what I was drawing before. Let me do it one more time. Go up, down like that. You see the kinks that travel away. So, well, let's make this thing go up and down continuously. So let's see that, see what happens. So what we get here is a bunch of kinks that travel all over the place. Now I'm going to pause it. Now I want you to notice what will happen. As you move away, these kinks here, they will start to overlap. So this line of the electric field, this line of the electric field, this line of the electric field, they will come closer and closer and closer to each other until eventually they will actually turn into one full line. So we're going to end up with one long line here, and that's going to loop around, come back up, and you're going to have a loop here. So everywhere I have my cursor is where I'm going to end up with these fields combining and forming a specific loop. Right, there's going to be a loop here, and then that loop will travel away from the charge. And we can show with math that that loop would travel using Maxwell's equations. We can show that that loop would travel away at the speed that is equal to the speed of light. Okay, so let me go back now to the drawings that I had. So here's my attempt at drawing all of these kinks, and then these kinks then combine and they form a single loop like that. And you can show that this loop will travel away at the speed v, which is equal to 3 times 10 to the 8th meters per second. We won't bother showing that that's the case, but this is what you would get. These kinks that would eventually overlap and form one single loop here. They would be traveling at the speed of light, speed c. And of course, you will have, as this charge moves, we would make this charge move up and down, up and down, up and down, and as it does so, it continuously produces these loops. And so somewhere out here you would have another loop that, oh, I wanted red. Somewhere out here you would have another loop that would look like this, and a little farther out you would have this loop that looks like this. But now let's put something. See, if you have, let's add direction to these loops. If you have this is where you have the electric field at points like that, then you have electric field at points like this. That implies that the electric field here along this loop would point like that. Maybe I should do it in a different color. So here electric field would point like that, therefore here it would point like this, it would point like that, and so here it would point like this. So the electric field here would loop around like this. Electric field here would loop around like this. And on the other side, just for the completeness, you would also have another loop. Since the charge moves up and down, these these loops travel away, you would end up with a bunch of these loops that look like this, and then you would have the electric field that, what does it do here? So it goes like this and goes up, so I would have something like this and it comes back, goes this way, goes back, so the outside points up, the outside here points up, and the inside points down. Did I get this right? Well, it's whatever. So we end up with these loops. Now, if you move farther and farther away, what you will notice, let's slide this out, as the charge continues to move up and down, and these loops continue to move away at the speed of light. If you get far enough away, what you will see is that the line here of the loop becomes nearly vertical, and it goes out and it does something, loops around and comes back and comes this way and then goes down and loops around and comes back up, and here the electric field points up, but here the electric field points down. And of course, somewhere over here you would have another loop that does something very similar, so you'd have this loop goes up and loops around eventually, comes back down, and then goes this way, and then loops around, comes back, and so what you would have is the electric field that does this. And so let's go on. What we get, the farther away you move, the more vertical this becomes, and you end up with these lines of the electric field, where one electric field points like this, and then the next one points like this, and then here you have this field that points like this, and then you have this field line that points like this. And these field lines, every single one of them is moving away at the speed of light, speed c. So maybe I'll put another one here. Every one of them is moving at speed c. All right, now I want you to look at it for a second. So if I have the electric field that points up here, or better yet, let's start on this side. If I have a line here, let's actually move it all the way there. There we go. Now, so what I have is electric field points up, then electric field points down. Well, what do I have between the lines of the electric field? Well, I have more of these lines, right? The electric field is not just a line. Electric field fills up the whole space. So I have another line that sits here. And I have another line that sits here, and I have another line that sits here, and I have another line that sits here. So I have many more lines here. But where I'm going with it is in the following place. So let's get rid of that. I'm going to redraw it. So let me move this up now. So the above can be drawn. All right. So again, remember that you have a field that points up, and then a field that points down, field that points up, field that points down. So I'm going to redraw it like this. And this finally might be, we might be getting to a certain point here. So let's draw a horizontal line that is going to indicate some kind of a level for us. Maybe this is the x-axis if we want it to be the x-axis. And then I would have these electric field lines where here I would have electric field that points up. I move a little farther down, I have electric field that points down. And this here would belong to the same loop, right? So this goes up, loops around, comes back down, loops around, goes all the way there, comes back up. So the electric field value here would be the same at every point. And so the length of this vector would be the same as the length of this vector. I move a little farther out and I have electric field that points up, and then this thing goes up and loops around, comes back, and here's electric field that points down, has the same value here as it did there because it's along the same loop. So it goes like that and so on. So let's add field here, a little farther down I have field here, here's field pointing like this, and here's field, electric field pointing like that. Now I want you to look at this picture. Here's the field that points up, here's the field that points down. between these two vectors, there are more vectors. But if I have a field that points up and then a field that points down, then at some point the field must be 0. Somewhere here between the two, the field is 0. I'm just going to put it that. And between this dot and this vector here, I have to have a field that actually decreases towards this dot. I would have that, and here I would have a field that increases. And if you wanted to, you could. Do I want to do it? I guess I'll do it. So you could put something like a, here's a loop here that does this. Here's a loop here that does this. Here's a loop here that does this. And I guess, so on. So, but I'm not going to draw all of these loops because that's just going to become too convoluted. And then between this field here and this field vector here, I have 0. I have to have 0 because if one point is negative, another one's negative, and the field is continuous, then there must be some kind of a change here. So there's a decrease, and then there's an increase, and then I think now we sort of see the pattern: increase, decrease, 0, increase, increase. And I'm going to add this. Well, let's put zeros. So this is 0, 0, 0, 0, and then let's draw this picture here where I have the vector, the electric field vector, that does the following. All right, and that will do. So what I have here is I have an outline of the electric field that looks just like a regular transverse wave. So I could now outline this as doing the following. And there it is. So you have the electric field and that electric field wave, and all of these vectors here, all of these vectors are traveling at the speed v equals c, the speed of light to the right. Now, recall from the very beginning of this little lesson that I mentioned that if you have a changing electric field, and that changing electric field specifically changes in time, then you end up with a magnetic field that is present. Now, here's an electric field, and this electric field certainly is not constant. If you were standing here at this point, and you are measuring this electric field as it comes towards you, you would measure that the electric field is changing as it comes towards you. And so you would have some sort of a time dependence of this electric field. And in fact, you could write out a wave equation where you would show that there's a dependence on, this is a traveling wave. This is nothing else but a traveling wave. And so if we wanted to, we could write this out as, oh, do I remember that? I guess I kind of do. So the electric field here would depend on both x and t, and you would have some maximum value of electric field. So I'm going to put here E max times, you could use sine or cosine, but I guess I'll use the cosine, and then you would have kx. This thing is traveling to the right, so it would have to be minus omega t. And so the electric field would depend on time. But electric field that depends on time has a magnetic field present. The magnetic field shows up. It can be shown that the electric field everywhere is perpendicular to the magnetic field, and that so that's one thing. The second thing that can be shown is that if you take the magnetic field, the magnitude of magnetic field, and you multiply it by c, you end up with the magnitude of electric field anywhere at any point along this wave. The third thing that can be shown, so this is the first thing, that the two are perpendicular. The third thing this is the second thing, that here's the relationship between their magnitudes. The third thing that can be shown is that the magnetic field, so in the first place, magnetic field is very, very, very much smaller in its magnitude than the electric field. But you could also show that this, oh, now which way is that pointing? Let's see. It's E cross B that gives me the pointing vector. So E cross B, okay, so the magnetic field would be perpendicular to a point like that. And I'm not drawing this to scale. I don't intend to draw this thing to scale, but you would have 90 degrees between the electric and the magnetic field. So here's the magnetic field, here's the electric field, and then let's just keep going. So then here I would have it pointing like this, then pointing a little farther out, then I would point like that. Then here we'll do this, and then I'll just keep going, I guess. So I'll draw that. And here it gets weaker, and here it gets stronger, but it points in the opposite direction. And then here it gets smaller. Here it increases, just like the electric field. And then here, this would point like that. Oh, could have drawn that one a little smaller, but anyways, there's that. And I'm almost done showing this. So we have a wave here. Actually, we have two waves, 90 degrees. Okay, and I can draw an outline of the magnetic field. So it would look like going over there, comes back, goes like this, out. Not too bad. And I guess if I were to put, maybe I'll add a coordinate system to this picture. So perhaps this is the Y, perhaps this is the X, and here's Z. So the electric field points along the Y-axis. The magnetic field points along the Z-axis. And the velocity and the direction in which the two move points along the X-axis. And this is what we call the electromagnetic wave. Now, how did we make this thing? How did we generate this electromagnetic wave? Well, we took a charge and we caused this thing to move up and down. And we ended up with this very nice looking wave. Now, in general, the charge doesn't have to move up and down. As long as you have a charge, so I'm going to put here in general. As long as you have a charge Q, it could be positive charge, it could be negative charge, makes no difference. As long as you have a charge Q. And this charge accelerates, you will produce an electromagnetic wave. And the electromagnetic waves have different shapes. They don't have to look sinusoidal in the sense that they don't have to look the way I drew them, the way I drew them here. You could have, these waves could have different shapes. But as long as you have a charge present, positive or negative, and that charge accelerates even for a brief period of time, you're going to end up with an electromagnetic wave that is generated away from that charge. Right, so if this charge here is accelerating, and it is because it's moving up and down, and so it's constantly changing its velocity, and therefore it has an acceleration, then off of this thing, you're going to have waves that travel at the speed of light. You're going to have an ENM wave here, and you're going to have an ENM wave here. All right, so there's that. Now you know how we generate electromagnetic waves. You should read the packet from the beginning to the end. It goes over the same process that I showed you in this video, and it fills in some of the blanks. And if there is a simulation listed somewhere, if there's a link to some animation or simulation in the packet, you should click on it and you should play with it to try to visualize what's happening here. All of this is just conceptual. I'm not going to ask you to calculate any things related to this, but you should understand the concepts. What I'll add to it, I should add to it the following. So let me move this up. If this charge moves up and down with a certain frequency, so let's say that you have this charge here and this charge moves up and down with a certain frequency, let's say frequency F, then you will get a very specific wave that has that frequency F. If the same charge moves up and down with a different frequency, F2, then you're going to end up with an electromagnetic wave that has a different frequency. So maybe something like this. So depending on what is the frequency with which this charge oscillates, you're going to get electromagnetic wave that has a very specific frequency here, or it has a very specific wavelength. All right, and so that leads us to the electromagnetic spectrum. And so I'm going to put here ENM spectrum. All of the following are different forms of electromagnetic waves. And so I'm going to start, actually, I don't think I have enough room here. So what I'll do is this: radio, microwaves, I think the next one is infrared. Then after that we have the visible. These are the forms of electromagnetic waves that our eyes can detect. Then we have UV, we have X-rays, and then we have gamma rays. all of these are electromagnetic waves. The difference between them is that here you have a long wavelength and here you have a very short wavelength. Somewhere in the middle you would have a wavelength that is somewhere in between the two. And as you move from left to right, the wavelength decreases, or as you move from left to right, the frequency increases. And that also implies that as you move from left to right, the energy packed per wave increases as well. But anyways, now you have the concept of an electromagnetic wave. You know how it is produced, how it is generated. Any accelerating charge gives you an electromagnetic wave.